control a 240 volts high-intensity discharge fixture with a photocell, several components are needed and the correct wiring practices must be followed. The first step is to understand the need for a step-down transformer. Because the high-intensity discharge fixture operates at 240 volts, but typical photocells are designed for lower voltages such as 120 volts or 24 volts, a step-down transformer is used to reduce the voltage to a level compatible with the photocell. Common transformer ratios include 240 volts to 120 volts and 240 volts to 24 volts. Secondly, selecting a photocell with a relay is very important. The photocell needs to be capable of switching a voltage that is compatible with the transformer's output. For example, if a 240 volts to 120 volts transformer is used, a photocell rated for 120 volts is required, along with a compatible relay. The relay acts as an intermediary switch, handling the higher voltage needed for the high-intensity discharge fixture while being controlled by the low-voltage signal from the photocell. Now let's look at the wiring diagram. On the high-voltage side, the 240 volt supply voltage is connected to the primary terminals of the step-down transformer. The secondary terminals of the transformer are then connected to the coil of the relay. This part of the circuit reduces the voltage from 240 volts to either 120 volts or 24 volts, depending on the transformer used. On the low voltage side, the photocell's terminals are connected to the secondary terminals of the transformer. When the photocell detects light or darkness, depending on its design, it closes its contacts. This action energizes the relay coil. When the relay coil is energized, it closes its high voltage contacts, which in turn supplies power to the high-intensity discharge fixture. For example, consider a scenario where there is a 240 volts high-intensity discharge fixture and a step-down transformer rated for 240 volts to 120 volts. The components needed include a photocell rated for 120 volts, a relay rated for 120 volts coil voltage and capable of switching 240 volts, and the step-down transformer with a 240 volts to 120 volts ratio. In this setup, the 240 volts supply is fed into the transformer, which steps it down to 120 volts. The 120 volts output is then connected to the photocell. When the photocell senses darkness, it allows the 120 volts to flow to the relay coil, which then closes, sending 240 volts to the high-intensity discharge fixture. When dealing with high-voltage wiring, it is imperative that it be performed only by a qualified electrician. All connections must be properly secured and insulated to prevent electrical hazards. Appropriate safety precautions, such as wearing insulated gloves and using insulated tools, must be taken when working with electricity. When connecting the 240 volt supply voltage to the primary terminals of the transformer, ensure that the connections are tight and properly insulated using wire connectors or electrical tape rated for the voltage. Similarly, when connecting the transformer's secondary terminals to the relay's coil, use appropriately sized wiring and secure connections. The photocell's terminal should also be securely connected to the transformer's secondary terminals. When installing the photocell, follow the manufacturer's instructions regarding its placement and orientation. Some photocells are designed to be mounted facing a certain direction to accurately detect light levels. The relay should be mounted in a suitable enclosure to protect it from environmental factors and to provide a secure location for wiring connections. When connecting the relay's high-voltage contacts to the high-intensity discharge fixture, use wiring that is rated for the voltage and current requirements of the fixture. Ensure that the connections are properly tightened and insulated. Before energizing the circuit, double-check all wiring connections to ensure that they are correct and secure. Use a multimeter to verify that the voltage levels at various points in the circuit are within the expected range. If any discrepancies are found, troubleshoot the wiring to identify and correct any errors. Once the circuit is verified to be correctly wired, carefully energize the circuit and observe its operation. The high-intensity discharge fixture should turn on when the photocell detects darkness and turn off when it detects light. If the fixture does not operate as expected, immediately de-energize the circuit and troubleshoot the problem. This could involve checking the photocell, relay, transformer, and wiring connections. Photocells come in various types, including those that activate in darkness and those that activate in light. The type of photocell used should be selected based on the specific application requirements. For example, if it is desired to have the high-intensity discharge fixture turn on at dusk and turn off at dawn, a photocell that activates in darkness should be used. Conversely, if it is desired to have the fixture turn on during the day and turn off at night, a photocell that activates in light should be used. Relays also come in various types, including electromechanical relays and solid-state relays. Electromechanical relays use a physical coil and contacts to switch the circuit, while solid-state relays use electronic components to switch the circuit. Solid-state relays generally offer faster switching speeds and longer lifespans compared to electromechanical relays. The choice of relay type depends on the specific application requirements and the desired performance characteristics. Transformers are available in various sizes and voltage ratios. The transformer should be selected based on the voltage requirements of the high-intensity discharge fixture and the available supply voltage. The transformer should also be sized to handle the power requirements of the fixture. When selecting wiring for the circuit, it is important to use wiring that is rated for the voltage and current requirements of the components. The wiring should also be suitable for the environmental conditions in which it will be installed. For example, if the wiring will be exposed to moisture or sunlight, it should be rated for outdoor use. In addition to the components mentioned above, other safety devices may be included in the circuit to protect against electrical hazards. These devices may include fuses, circuit breakers, and ground fault circuit interrupters. Fuses and circuit breakers are designed to protect against overcurrent conditions, while ground fault circuit interrupters are designed to protect against ground faults. It is important to select and install these safety devices in accordance with applicable electrical codes and standards. Proper grounding of the electrical system is also essential for safety. Grounding provides a path for fault current to flow back to the source, which helps to protect against electric shock. The grounding system should be installed in accordance with applicable electrical codes and standards. Regular inspection and maintenance of the electrical system are important to ensure its continued safe and reliable operation. This includes checking wiring connections, inspecting components for damage, and testing safety devices. Any problems that are identified should be promptly corrected by a qualified electrician. When working with electricity, it is important to always follow safe work practices. This includes wearing appropriate personal protective equipment, such as insulated gloves and safety glasses, and using insulated tools. Before working on any electrical circuit, always de-energize the circuit and verify that it is de-energized using a voltage tester. Never work on electrical circuits while standing in water or on a wet surface. Be aware of the potential hazards associated with electricity and take steps to minimize the risk of injury. The National Electrical Code, or NEC, provides comprehensive guidelines for the safe installation of electrical systems. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It is important to be familiar with the applicable requirements of the NEC when working with electrical systems. Local electrical codes and regulations may also apply. These codes and regulations may vary depending on the location. It is important to check with the local authorities to determine the applicable requirements. Continuing education and training are essential for electricians to stay up to date on the latest technologies, codes, and safety practices. There are many opportunities for electricians to participate in continuing education and training programs. These programs can help electricians to improve their skills and knowledge and to stay safe on the job. By following these guidelines and taking appropriate safety precautions, it is possible to safely and effectively use a photocell to control a 240 volts high-intensity discharge fixture. Remember, safety should always be the top priority when working with electricity. Always consult with a qualified electrician if you have any questions or concerns. High-intensity discharge lamps, or HID lamps, are a type of electrical gas discharge lamp which produces light by means of an electric arc between tungsten electrodes housed inside a translucent or transparent fused quartz or fused alumina arc tube. This tube is filled with both a noble gas, such as xenon, and often also metallic salts. The noble gas enables the arc's initial strike. Once the arc is started, it heats and evaporates the metallic salts, which then greatly increase the intensity of the light produced by the arc and reduce its power consumption. High-intensity discharge lamps require electrical ballast to regulate current and voltage, provide starting pulses, and maintain proper operating conditions. The most common types of high-intensity discharge lamps include mercury vapor lamps, metal halide lamps, and high-pressure sodium lamps. Each type has its own characteristics, such as light output, color rendering, and energy efficiency. Mercury vapor lamps were one of the earliest types of high-intensity discharge lamps. They produce a bluish-green light and are often used for street lighting and industrial lighting. However, they have relatively poor color rendering and are being phased out in favor of more efficient and environmentally friendly alternatives. Metal halide lamps offer improved color rendering and higher light output compared to mercury vapor lamps. They contain metal halide salts in addition to mercury, which enhances the color spectrum of the light produced. Metal halide lamps are commonly used for indoor and outdoor lighting applications such as sports stadiums, retail stores, and architectural lighting. High-pressure sodium lamps are the most energy-efficient type of high-intensity discharge lamp. They produce a yellowish-orange light and are often used for street lighting and security lighting. While their color rendering is not as good as metal halide lamps, their high efficiency makes them a popular choice for applications where energy conservation is a priority. When selecting a high-intensity discharge lamp for a particular application, it is important to consider factors such as light output, color rendering, energy efficiency, and lifespan. It is also important to choose a lamp that is compatible with the existing ballast and fixture. High-intensity discharge lamps typically have a longer lifespan compared to incandescent lamps, but they do require periodic replacement. The lifespan of a high-intensity discharge lamp is affected by factors such as operating conditions, lamp type, and ballast type. It is important to follow the manufacturer's recommendations for lamp replacement to ensure optimal performance and safety. In addition to their use in lighting applications, high-intensity discharge lamps are also used in other applications such as automotive headlights and projection systems. In these applications, the high light output and compact size of high-intensity discharge lamps make them a desirable choice. The use of photocells to control lighting systems offers several benefits, including energy savings, convenience, and security. By automatically turning lights on and off based on ambient light levels, photocells can help to reduce energy consumption and lower electricity bills. They also provide convenience by eliminating the need to manually switch lights on and off. Additionally, photocells can enhance security by ensuring that lights are on during nighttime hours, which can deter crime. Photocells are available in a variety of styles and configurations to suit different applications. Some photocells are designed to be mounted on a wall or pole, while others are designed to be integrated into a lighting fixture. Photocells can also be wired to control multiple lights or circuits. When installing a photocell, it is important to choose a location where it will accurately detect ambient light levels. The photocell should not be shaded by trees or buildings, and it should not be directly exposed to artificial light sources. The photocell should also be mounted in a way that prevents water from entering the device. Regular maintenance of photocells is important to ensure their continued reliable operation. This includes cleaning the lens of the photocell to remove dirt and debris, and checking the wiring connections to ensure that they are secure. Any problems that are identified should be promptly corrected to prevent further damage or failure. In conclusion, using a photocell to control a 240 volts high-intensity discharge fixture requires careful planning, proper wiring, and adherence to safety precautions. By following the guidelines outlined in this discussion, it is possible to safely and effectively implement this type of lighting control system. Always consult with a qualified electrician if you have any questions or concerns. The selection of appropriate components, including the step-down transformer, photocell, and relay, is crucial for ensuring the safe and reliable operation of the lighting system. The wiring connections must be properly secured and insulated to prevent electrical hazards. Regular inspection and maintenance of the system are essential for identifying and correcting any problems that may arise. By following these best practices, you can enjoy the benefits of automated lighting control while minimizing the risk of electrical accidents. When working with electrical systems, it is always better to be safe than sorry. If you are not comfortable performing the work yourself, it is best to hire a qualified electrician to do the job. Electrical work can be dangerous, and it is important to take all necessary precautions to protect yourself and others from harm.